So I just remember there. Thanks very much for reminding me to start the recording, right? So once again, let me start over, right? Okay, so we're looking at some of the practice problems here now from on the Laplace transform from what were suggested in the course webpage, right? And these problems are very important in terms of being able to solve some of these questions, to apply the techniques, because it's not just enough to just go through the theory, right? So you have to learn how to apply the theory, and it might come, you know, in different ways. So you have to practice as many problems as possible, right? So during the tutorials, I would go through as much questions as possible. And once time allows, I will also try to go through some of the past exam questions. So you should be, you should have access to those past exam questions because it's there in the course webpage. So you could look at some of those questions, you could look at some of the solutions. The thing about it is those questions on them, you need to practice those types of questions, especially for the final exam, right? So in the actual solutions in the Finan, right? Some of these steps are missing. So I try to write out as many steps as possible to guide you, right? So as I said before, in order for integral to converge, the integral must have a finite value, right? Once the integral gives you an infinite, like infinity, for example, it means that the integral will diverge. So we check in here now. So this integral here, this function here is of this form here, right? Dx over ax plus x squared. Ax is basically a constant, right? So the rule for this, when you're integrating anything of this form here, would be 1 over the constant, the tan inverse, x over a. So the x over a would be the argument, right? Plus a constant, because remember here we have limits, but in the rule here is an indefinite integral. So once you're integrating an indefinite integral, the constant will come in. Of course, when you're doing the integral with limits, the definite integral, you won't have a constant, right? So if we match it up here, we'll see that what squared will give you 1, right? 1 squared will give you 1. So basically a is 1. X squared is t squared, right? So if we apply that here with the limits here, we'll get the integral, right? R going to infinity between R and 0, 1 over 1 plus t squared dt is actually the tan inverse of t, R going from, the limit of R going to infinity between R and 0, right? So now here I draw a little graph here, right, of the tan inverse graph there, right? And this is the general tan inverse graph, right? It between, on the y-axis, it between pi over 2 and minus pi over 2. So these are like the asymptotes there. So as t approaches infinity here, it gets closer and closer to the pi over 2 line here. And similarly, it gets closer and closer to the minus pi over 2 line as t approaches minus infinity, right? So this is the graph here of tan inverse t, right? So R here, remember R, the upper limit approaching infinity. So therefore, you're going this way along the t-axis, so it will get closer and closer to pi over 2. So therefore, the limit would be pi over 2, right? And then when you plug in 0, right, because you have to minus tan inverse 0. Tan inverse 0 is, well, you see 0 going through the origin here, so tan inverse 0 is 0. So pi over 2 minus 0 is pi over 2. Pi over 2 is a finite value, therefore the integral converges to pi over 2, right? Right, so let's look at another one here. Determine whether the integral between infinity and 0, e to the minus t cos e to the minus t dt converges. If the integral converges, give its value, right? So here now we could use what you call a substitution, right? So when you look at the integral here, you could let u equal e to the minus t, right? So therefore, if you differentiate u with respect to t, you get minus e to the minus t dt, right? So basically, du, right, minus du would be e to the minus t dt, right? So we're ready to make our substitution now. So where you have e to the minus t, you put in u, right? So here you're getting u, right? And you want to change from u, t to u, right? So minus e to the minus t dt, that is this term here together with this one here, right? Right, if you put them side by side here, that will be minus du. And this will be cos u. So you have minus cos u du. And your upper limit here now, remember, is infinity here, but u is e to the minus t. So you have to replace the upper limit here with e to the minus r, because you're taking the limit as r approaching infinity. And the lower limit would be 1, right? Because e to the 0, anything to the 0 is 1, right? So when you integrate cos u, you get sin u, but you have a negative in front, so you have negative sin u. And then you apply the limit e to the minus r1, r approaching infinity. So this here, of course, if r approaching infinity here, that would be e to the negative infinity, right? Which is 0, right? So this term here, and you have a minus in front of it. So I put it on the right-hand side. And then you have the minus sine 1. So I put that in front here, plus sine 1. So this term here will approach 0. So the answer will just be sine 1. So the integral converges to sine 1. Sine 1 is a finite value, right? So we're looking at another one. Determine whether the integral between infinity and 0, t over 1 plus t squared dt converges. If the integral converges, give its value, right? So again, I'm using a substitution here, taking the denominator 1 plus t squared to be u. So therefore, I want to change my integration from dt to du. So du will be 2t dt. So du over 2 will be t dt, which is the part on top here. So I will replace that part here on top by du over 2, right? And of course, the 2 here is a half, 1 over 2. I could pull that on the outside, right? And then I have u at the bottom, because 1 plus t squared is u, right? So this is a straightforward integral here. This is ln u, right? And the upper limit is r and the lower limit is 1, right? Because if t is 0, if I replace t with 0 here, u will be 1 plus 0. So the lower limit is 1. And the upper limit, of course, if t is infinity, u will be infinity. So I replace the top with r, and I let this approach infinity, right? So this will give me the ln r, right, minus ln 1. ln 1 is 0, right? So you just get ln r by half, and r approaching infinity. So you should be kind of familiar with the ln graph, right? So the ln graph will go something like this, right? So as you move to the right, meaning r approaching infinity, what would happen here, right? The graph going higher and higher. So what would happen here is this ln infinity will be infinity. So therefore the integral is divergent. The ln graph is basically the log graph in base E, right? Using the definition, find the Laplace of t minus 5 if it exists. If the Laplace transform exists, then find the domain f of s, right? So let's look at this here, the Laplace. We're using the definition of the Laplace. Remember, the definition is the integral, right? E to the minus st by ft. In this case here, ft is t minus 5, right? So what we could do a little integration by parts here. We could call u t minus 5, we could call dv e to the minus st, right? So du will be, you integrate with respect to t here, you will get 1, right? And then v will be the integral of this, so you have to divide by minus s, which is minus e to the minus st over s, right? So if you write it back now, remember you're taking the limit as r tends to infinity, the integral between r and 0. So you take the limit on the outside, and this is your uv, right? And this is your v du. Remember, right, your uv, right? Remember this is t minus 5, e to the minus st over s and a negative in front of it, right? And you're taking that between r and 0. And then you want a minus v du. So that'll be e minus minus e to the minus st over s, right? Which is basically plus, right? And the 1 over s, you could pull it on the outside because the integral is basically has nothing to do with the s, so the s is a constant. The integral is with respect to t, right? So this is a straightforward integral here, e to the minus st, right? So when you integrate this here, you'll get e to the minus st over minus s, right? And then you have another s here to take. So that will be s squared. And you could pull your minus sign on the outside. And you evaluate the limit between r and 0, right? Now on this side here, on the left-hand side, remember r had to go where t is. So when you put r here, the upper limit will be minus r minus 5 e to the minus 5, sorry, minus sr over s, right? And then you put in the lower limit here, you will have a minus minus, so it will be plus. And if you put a 0 here, and then you put 0 here, that will be 1, right? So that will be 5 over s. So you have your plus 5 over s here. And then you have your minus e to the minus st over s squared on the right-hand side. And when you put r in here, and r tending to infinity, remember this will approach 0. And when you put 0 here, right, you'll have to minus minus 1 over s squared. So you end up with 1 over s squared plus this term here, 5 over s. This term here will also approach 0 because of the negative s here, right? So your domain of fs is s would be greater than 0, right? Because if s is anything 0 less, here, of course, here will be undefined, right? 43.8. Using the definition, if it exists, right? So if the Laplace exists, right? Because you remember it had conditions in order for the Laplace to exist, right? The function had to be it had to be piecewise continuous, and it had to be of exponential order, right? We have a piecewise function here, right? But we don't know if it's of exponential order, so we're going to check and see, right? So this function here is 0 between 0 and 1, and it is t minus 1 for t greater or equal to 1. So you could apply the definition here, the integral between infinity and 0, e to the minus st, ft, right? And your ft is 0, right? Between 1 and 0. So if you're putting that into this formula here, then your limits will have to be between 1 and 0, and then you have to add, right? The next value for the function between infinity and 1, right? But remember, if you're multiplying a 0 function by anything, you'll get 0. So that term will just drop off. So all you will get is the integral between infinity and 1 with the function defined to be t minus 1, right? And here you do your usual integration by parts, right? So you call t minus 1u, you call e to the minus s t dv, right? So du will be 1, v will be e to the minus st over minus s, right? And your uv will be minus t minus 1 over s e to the minus st. And your v du will be minus e to the minus st over s. So you could, the minus will give you a plus 1 over s e to the minus st, right? Now you apply the limits here. Well, when you put r is, you replace t by r here, right? So that you'll get this here, r minus 1 e to the minus sr over s. And then you put in 1, the lower limit, right? So you get e to the minus s. But when you put 1 here, that will be 1 minus 1 is 0. So 0 by anything is 0. So that term will just vanish. So you notice you just have the term with the upper limit here. And then when you integrate e to the minus st, you'll get a minus 1 over s at the bottom. You pull that out, so you get minus 1 over s squared, and then you take the limit here of this function here, e to the minus st between r and 1. This term here approaching 0, right? Here now when you put r here, right? You'll get a minus e to the minus sr over s squared, that is this term here, right? And then you have to minus, which is plus 1 over s squared e to the minus s, which is this term here. So we just rearrange them, right? And this term here will also approach 0 because r approaching infinity, right? So you end up with e to the minus s over s squared, and s again, the domain here is of fs is s greater than 0, right? Right, so take your time there and look at it, right? So let me just pause for a few moments. Okay, so let's continue. Using the definition, find the Laplace of ft if it exists. If the Laplace transform exists, then find the domain of fs. So again, you have a piecewise function. It have three definitions: 0, t between 0 and 1. The function is t minus 1, t between 1 and 2. And the function is 0 for t greater or equal to 2. So you break it up into three parts then, because it's piecewise continuous and it's defined by three different functions, right? For each part, basically. So the only part that will really give us a contribution, because all the other parts have 0 in them. So anytime you multiply this here by, if ft is 0, then e to the minus st by 0 is 0. So you won't have to evaluate that, right? So you're focusing between 1 and 2 here, right? So your limits here is 2 and 1, t minus 1, e to the minus st. And we take u to be t minus 1, and we take the v to be e to the minus st, right? And then we perform our integration by parts, right? And your uv will be minus t minus 1, e to the minus st over s, like what we did before. So you could write down the steps, right? And your VDU will give you this part here, minus 1 over s squared e to the minus st, and then you're taking the limits between 2 and 1. So if you're putting 2 here, right, that will be 2 minus 1 is minus e to the minus 2s over s. So that is this term here, right? The first term. And then you're putting the 2 here in this term as well. So you have minus e to the minus 2s over s squared. So that is the second term, right? And then you have to subtract with the lower limit then. So you'll have to minus, right? So minus when you put in, so this will be a plus 1 minus 1, which is 0. So it doesn't make sense putting in the 1 here, because anything by 0 is 0, right? And then the next term now, minus, which will be plus e to the minus s over s squared. So that is this term here. So that is how you end up with the result here, the Laplace transform. S is not equal to 0. Let n be a positive integer. Using integration by parts, establish the reduction formula. So the integral, right? The indefinite integral t to the n e to the minus st dt is minus t to the n e to the minus st over s plus n over s, the integral t to the n minus 1 e to the minus st dt for s greater than 0, right? So we want to show that. So here now we just use our integration by parts. So dv is e to the minus st, and u is t to the n. So v will be e to the minus st over minus s. Du will be n t to the n minus 1, right? So your uv will be t to the n minus t to the n, because you have a negative here, e to the minus st over s. And then you'll have to minus v du, right? That is these two terms here. So you notice you'll get n t to the n minus 1 e to the minus st over s, and you pull the negative, right? So a negative will give you a positive. And then of course you could factor the n and the s. because the integral has nothing to do with the n and the s. You treat those as constant. The integral is with respect to t. So you would have under the indefinite integral t to the n minus 1 e to the minus st dt for s greater than 0. So this is the result here. Right? So you could show it in just 2 steps. Solve, sorry, for s greater than 0 and n a positive integer, evaluate the limit t approaching 0, t to the n, e to the minus st. So that is 1. And the second one here, part B, the limit of t approaching infinity, t to the n, e to the minus st. So we take any first limit here. So the limit of t approaching in 0, t to the n, e to the minus st. This could be rewritten, right? You could put e to the minus st in the denominator position. So you'll have t to the n over e to the positive st, right? And then if t approach 0, you'll get 0 on top. And if t approach 0, you'll get e to the 0, which is 1. So this limit here works out to be 0, right? The second limit now, let's look at the second limit. So you have the same function here, but you're taking the limit as it approaching infinity this time. So you write the function in a similar way to the part A, the limit of t approaching infinity, t to the n, e to the st. But notice, if t approaching infinity, you will get infinity on top. And if t approaching infinity, you'll get e to the infinity at the bottom. So you'll get infinity at the bottom as well. So anytime you have a 0 over 0 or infinity over infinity form, you can't evaluate a limit like that. We say that is indeterminate, right? So what you could do here, you could apply something called L'Hopital's rule, right? Where you could differentiate the top and bottom separately, right? And then take the limit. So if we differentiate the top, right, we'll end up with respect to t, we'll get n to the tn minus 1. And if we differentiate the bottom with respect to t, we'll get s e to the st, right? And if we let this approach infinity, you're still getting infinity over infinity. So that is still indeterminate, right? So we continue top and bottom differentiation, right? So we we differentiate a third time. So you will have to multiply by n minus 1, and you'll have t to the n minus 2 on top, and then you'll have to multiply by s here, so you'll get s squared e to the minus st, right? So what will happen there? You will still have an indeterminate form here. So what we do, we continue differentiating, right? So if you notice, you see a pattern here. You'll have n minus 1, n minus 2, and eventually, right, this is the form of n factorial. It will differentiate all the way down to 2 by 1, right? So that is n factorial basically, right? And then what will happen in the denominator? You'll get another, you'll keep getting s's. So for each factor on top here, you'll get s. So you get s by s by s by s all the way down to 1 over s. So you could separate each factor on top over an s then. And then, well, this will be s to the power n basically, because if this is n factorial, by e to the st, right? It's from here to here. Right, and this from here to here is n factorial. So what you have here, right, you have the limit at t approaching infinity, n factorial over s to the n, e to the st. Now this n factorial here, right, has nothing to do with your t. This don't have t in it at all, right? So the only part that you're dealing with here is the denominator. You have t here, e to the st. So what will happen here? Your denominator will approach infinity, right? So once your denominator approaches infinity, it gets larger and larger. The fraction will get smaller and smaller. So this limit here will be 0, right? So that is how you evaluate that limit. Use the previous results. That is what we just derived here, right? To derive the reduction formula for the Laplace transform of ft is t to the n. So we have, remember, the Laplace at t to the n is n over s. The Laplace at t to the n minus 1 for s greater than 0. So that is part A. I want to derive that. Secondly, part B, I want to find the Laplace at t to the k for k going from 1 to 5. So you want the Laplace at t, the Laplace at t squared, the Laplace at t cubed, t to the power 4 and t to the power 5, right? And finally, in this part here, part C, formulate a conjecture as to the Laplace transform of ft, right? Tn with n a positive integer, right? So let's look at the first one here. Remember, by definition here, this is the limit of r tending to infinity between r and 0, the limit of the integral, right? Replace the function by tn and e to the minus 3t, right? And we know that we call u t to the n, we call dv e to the minus st. So du will be n t to the n minus 1 and dv will be minus e to the minus st over s. And our uv will be minus t to the n e to the minus st over s. And you have to take the limit for that between r and 0. And then v du will be minus, you remember you have to minus, so minus is a plus. So you could pull the n over s on the outside, and you'll have t to the n e to the minus st. And you're taking the integral of that between r and 0. So this here, right? This here is basically the definition this part here on the right is the definition, just like t to the n e to the minus st, but just instead of having t to the n, you have t to the n minus 1. So this here is the Laplace at t to the n minus 1, and you have a n over s on the outside, right? Of course, we know that this term here will work out to 0, right? Because if you're putting r here, right? Since this is a negative in the exponential position, the first value here will approach the 0. The second value, you have to minus t to the n, and you're applying t to be 0. So 0 by anything is 0. So from here, you would get 0, right? So it's just this part would survive. So that is basically the limit, which is the definition of the Laplace at t to the n minus 1. And you have to multiply that by n over s on the outside, right? For s greater than 0, right? So now we could apply the rule here, t to the n, the Laplace at t to the n is n factorial over s to the n plus 1. So t to the 1, wherever n is, you put 1, so you'll get 1 over s to the power 1 plus 1 is 2. T to the power 2, you'll get 2 factorial over s to the power 3, and 2 factorial is 2. And then the Laplace t to the power 3, what you'll get here, you'll get 3 factorial over s to the power 4. So that is 6 over s to the power 4. T to the power 4 is 4 factorial over s to the power 5, which is 24 over s to the power 5, and the t to the power 5 is 5 factorial over s to the power 6, which is 120 over s to the power 6, right? Part C now. So you have the Laplace of t to the n is n over s. The Laplace of t to the n minus 1. So if we substitute the definition repeatedly, right? So for this part here, right? If we differentiate this part here, we go get n on n minus 1 over s on the outside, and we'll have a Laplace t to the n minus 2, right? And then we do that again, we'll have a n minus 2 over s, Laplace t to the n minus 3. Eventually, we'll end up with 2 over s, the Laplace t, right? Because remember, this term here on the outside, the power here is always 1 less. So if this term here is 2, what is 1 less than 2? The power here will be the Laplace t to the power 1, right? And the Laplace t is 1 over s squared. So you'll have n minus 1 all the way down to 1. So that is n factorial. And from here to here, you'll get s to the n. Oh, you'll get here s to the, because you're going down to 2, right? So you'll get 1 less than s to the n. So you'll get s to the n minus 1. Right? So remember here, n down all the way down to 2, right? I could write this a better way. What I could do here, I could separate this one, 1 over s squared as 1 by 1 over s. So you notice s in the denominator all the way down to this s here. Right? N all the way down to 1 here, the first one, right? So that is n minus 1, n minus 2 all the way down to 2 by 1. So that is n factorial. And then this will be s to the power n. And then you have an additional s here. So that will be s to the n plus 1. Right? So I hope that makes it a little easier for you so you could see it clearly. Right? Okay. Using the linearity property of Laplace transform to find the Laplace of 5e to the minus 7t plus t plus 2 e to the minus, e to the 2t, right? So now we're solving a problem here, right, where we are applying the linearity property here with the Laplace. So we taking the Laplace 5e to the minus 7t plus t plus 2 to the 2e to the 2t. So remember the linearity property, you pull the 5 on the outside, so you're taking the Laplace of e to the minus 7t. And then you're adding the Laplace of t, that is the middle term. And then you're pulling out the constant 2, and you're taking the Laplace of e to the 2t. So recall that e to the minus 7t is 1 over, the Laplace of that is 1 over s plus 7. right? And the Laplace of t is 1 over s squared, and the Laplace of 2t is 1 over s minus 2. But you have 2 here to multiply it by, so it will be 2 over s minus 2. Right? And your domain here, s must be greater than 2. Right? Because in order for it to be defined, because of this factor here, s minus 2. Use the Laplace table again to find the Laplace at 2e to the t plus 5. So again, you're using the linearity property. So that will be 2 Laplace e to the t plus 5 the Laplace 1. And the Laplace 1 is basically t to the 0. Remember this, eh? So we're doing all this here for you to remember the rules and so that you can apply the rules. So this will be 0 factorial over s to the 0 plus 1. So 0 factorial is defined to be 1. So this will be 1 over s. That is how you get this here. Anything to the 0 is 1. So t to the 0 is 1. So this is another rule here that is derived from the Laplace at t to various powers then. So you end up here e to the t, the Laplace of that will be 1 over s minus 1, and you have to multiply by 2. So you have 2 over s minus 1 plus 5 over s, and s must be greater than 1 here, right, in the denominator here, because this here can't be 0. Otherwise, you'll have an undefined value. Okay, so we come to some problems here involving the Heaviside function. Remember the Heaviside step function? So you want to take the Laplace of e to the 3t minus 3 h t minus 1, right? So, some notations might use common s. Normally I would use capital S, right? In the lecture notes you have capital S. So maybe I should leave it as capital S. In some texts you might see the Heaviside with a U, right? So don't let that confuse you, right? So let me leave it as a capital H then, right? Right. So if you notice, the Heaviside function is defined a certain way, right? So I have an example down here. Oh, I didn't write it. Right. Right. So this is the Laplace e to the 3t minus 3 h at t minus 1. So what you could do here, you could take the Laplace of the 3t minus 3 and write it as 3t minus 1, because you want this part here, the t minus 1, to match up with this t minus 1 here, in order to apply the rule then, in order to find the Laplace, right? So the rule states the Laplace y t minus t naught h t minus t naught is equal So e to the minus s t naught, the Laplace yt. So just for a minute, look at that rule there. So yt minus t naught, this is your function. Ht minus t naught is your heavy side, right? So whatever your function, your t naught is here. So your t naught here, as you see in here, is 1, right? So your function has to be defined in such a way to apply the Laplace for this to be something t minus 1. So that is why we separate we factor out the 3. So we have t minus 1 here, right? And if it's in that form and you're taking the Laplace, so this basically is in the form, right? So therefore you just e to the minus s t naught. So what is t naught? T naught is 1. So that will be e to the minus s by 1. Hence why we have this here. And now you're taking the Laplace of just the function, right? Without your instead of yt minus t naught, you just have yt, right? So yt is just 3t, e to the 3t. And we know that the Laplace of that is 1 over s minus 3. So the answer here is e to the minus s over s minus 3, where s is the domain of f of s is s greater than 3. Right? Right. So we want to take the Laplace of sine squared omega t. Right? So we want to find it. We know the Laplace of sine omega t, right? But we don't know the Laplace of sine squared omega t, right? So remember the Laplace of sine omega t is omega over s squared plus omega squared, right? But that is for sine omega t, right? But here now, so we have to apply some kind of identity in order to do this, right? So what I say, using the identity 2 omega t is cos squared omega t minus sine squared omega t, right? And the cos squared omega t, you can write that as 1 minus sine squared omega t minus sine squared omega t, which is 1 minus sine squared omega t, right? So 2 sine squared omega t would be 1 minus cos 2 omega t. So sine squared omega t, we could use the trigonometric substitution 1 minus cos 2 omega t over 2. Right? So this is much easier to deal with because it don't have no power here for the trig function. Right? We don't know how to find the power, the Laplace of a trig function with a power. So here now, if you use the linearity property, you'll just be taking a half the Laplace of 1 minus a half the Laplace of cos 2 omega t, which we know. So that will be 1 over 2 by 1 over s minus 1 over 2 by s over s squared plus 2 omega squared. So basically you'll get here half 1 over s minus s over s squared plus 4 omega squared, right? And your domain is s greater than 0. So again, we find in the Laplace here of sine 3t cos 3t, right? So what we could probably do here is use a double angle formula, right? So you have sine 2t is 2 sine t cos t, right? You really want 3t and 3t here. So if you have 3t, remember here, whatever you have here, you have that double on the outside. So sine 6t is 2 sine 3t cos 3t. So when you divide that by 2, you'll get your sine 3t cos 3t. So you can make your substitution now. The Laplace of sine 3t cos 3t is really the Laplace of sine 60 over 2, which is a half the Laplace of sine 60. And the Laplace of sine 60 is 6 over sine squared, 6 over s squared plus 6 squared, which is 6 over s squared plus 36 by a half, right? So you'll end up with 3 over s squared plus 36 and s greater than 0. Okay. Right, so that was a lot of work there with the Laplace, taking the Laplace, and now we're looking at the inverse Laplace, right? From what we did in the lecture notes, right? We could be able to figure out some of these inverses. So you want to find the Laplace inverse of 10 over s squared plus 25 plus 4 over s minus 3, right? So again, you could use the linearity property. So you take that, you break it up as the Laplace inverse of 10 over s squared plus 25, right? So now you're going from your s variable. You remember when you was taking the Laplace, you was going from t to s. Now you're taking the inverse, so you're going from s back to t, right? So you have the Laplace inverse of 4 over s minus 3. Remember this here, this 25 could be written as 5 squared. So which means you'll have to have a 5 on top here, right? So if you have a 5 on top here and you want 10, then you have to multiply by 2. So you see a factor out of 2 on the outside, right? So you have your 5 over s squared plus 5 squared, and you're taking the Laplace of this. So this would be sine 5t multiplied by 2. And the Laplace inverse of 4 by the Laplace inverse of 1 over s minus 3 is 4 by e to the 3t, right? And your time variable must be greater or equal to 0. Because time can't be less than 0. Using the partial fraction decomposition, I want to break up this inverse, right, into partial fractions in order to make it easier for you to find the inverse. So remember the decomposition, you have 2 simple factors in the bottom here. So you have 12 over the 2 simple factors, a over 1 of the factor plus another constant over the other factor. So if you multiply it throughout by the 2 factors, you will get 12a into s plus 1 plus b into s minus 3, right? And you want to find the constants. So if you put s equal minus 1, this constant here will drop out. You'll get minus 4b is 12. So b is minus 3. And likewise, if you put s equal 3, this part here will drop out with the b. So you'll get 3 and 1 is 4, a is 12. So which means a is 3, right? So your Laplace inverse of that function there in s could be broken into the Laplace inverse of 3, because your a is 3 over s minus 3 minus 3, because b is minus 3 over s plus 1. And now you could just pull out the 3. So you have the 3 Laplace inverse 1 over s minus 3 minus 3 Laplace inverse of 1 over s plus 1, and then you take the inverse of 1 over s minus 3, that would be e to the 3t, and you have your 3 outside, so you multiply it, and then your minus 3 multiplied by e to the minus t for t greater or equal to 0. Okay, so this one, another Laplace inverse here, 44.20 Using the partial fraction decomposition, find the Laplace inverse of 24 e to the minus 5s over s squared minus 9, right? So when you're finding the decomposition using your partial fraction, this part here cannot be part of the decomposition. Your e to any power s cannot be part of your decomposition. So your decomposition here is really your 24 over s squared minus 9. And this here is the difference of 2 squares. So that is 24 over s plus 3, s minus 3. So the partial fraction decomposition for that would be a constant over s plus 3 plus another constant over s minus 3. Right? So 24 will be equal to, when you multiply throughout by s plus 3, s minus 3, you'll get s minus 3 by a plus b by s plus 3. And to solve for your constants, you put s equal to 3. You'll get 6b equal to 24, so b is equal to 4. And then you put s equal to minus 3, right? So you get minus 6a is 24. So a is minus 4. Right? So the negative, so this one is negative, the a is negative, and the b is positive. So what I'll do now, you remember the minus 4 is over s plus 3. So I write that on the right hand side. So minus 4 over s plus 3, and I take this one with the positive value and I write it on the left hand side. So you just have to be cautious in doing that, to make sure you don't mix up the constants over which factor then. Otherwise, the end result will differ, right? It's just a convenient way. I like to put my positive values in front, my negative values after, right? It just looks more orderly, right? So the 24 over s plus 3, s minus 3, this is the decomposition for it, right? So remember now, you have to multiply this back by e to the minus 5s. So this here, you have to multiply this by e to the minus 5s, s minus 3. And you can take the 4 on the outside. And likewise, you have to do it with this one here. So you take the minus 4 on the outside. And then inside, you have the Laplace inverse of e to the minus 5s over s plus 3. And then here you use this rule here again, right? So the Laplace, the heavy side, t minus t naught of a function y, t minus t naught, is e to the minus s t naught ys. And an alternate we are writing this here is the Laplace inverse of e to the minus s t naught ys is the heavy side t minus t naught y t minus t naught, right? So what we using? We're using the alternative way of this here because we're doing the inverse. If you notice, these functions here mimic this the inverse here based on the formula. You have your t naught here in the first instance here is 5, and here is 5. So you want some heavy side with t minus 5, y t minus 5, and you know what you'll get, right? So let's go through the first one here. So this one here, 4 Laplace inverse e to the minus 5s over s minus 3, right? So I could break up that. This is e to the minus 5s by 1 over s minus 3. So this here is my function, right? So this is 4. The Laplace inverse of 1 over s minus 3. That is e to the 3t, right? But because the function must be t minus your t naught, and your t naught here is 5. So it will be 3 to the t minus 5. And then the heavy side, of course, will be t minus 5. Similarly with the next one. You have e to the minus 5s by 1 over s plus 3. And this function here, right, the inverse of this function here is e to the minus 3t. And remember your heavy side at the coming to it, so your function in t here had to be not just yt, but yt minus t naught, and your t naught is 5, so it will be e to the minus 3t minus 5 by a negative 4 by your heavy side at t minus 5. And now you just combine all the results. So the Laplace inverse at 24 e to the minus 5s, s minus 3, s plus 3 in the denominator will be 4 by e to the minus e to the 3 by t minus 5 minus e to the minus 3 by t minus 5 by the heavy side at t minus 5. So this will be the combined result for t greater or equal to 0. So that was section 44. So section 45 now gives 45.1 to 45.4 gives the form of the partial fraction expansion for capital F of S, right? So that capital F of S is really the Laplace of f of t. No need to evaluate the constants in the expansion. However, if the denominator has an irreducible quadratic expression, then use the completing the square process to write it as the sum or difference of two squares. So you should be a little familiar with this here. What will be the partial fraction breakdown for this this expression here, right? You have two simple factors, but you have one repeated and one repeated, right? So when it repeated, you have to write it to the power 1, and then you write it to the power 2. And when it occurs 3 times as a factor, you write it to the power 1, 2, and 3. You understand? So you'll have a constant over s minus 1 plus a constant over s minus 1 square plus a constant over s minus 1 cube. And then for the repeated factor, you'll have a constant over s minus 2 plus a constant over s minus 2 squared. So you notice I use different constants, A, B, C, D, and E. Right. So here, in the second example here, 45.2, right? You have a simple factor, s minus 2, and you have a quadratic factor, right? But this quadratic factor is irreducible. So for the quadratic factor, you must have a constant by s plus another constant over that quadratic factor. And then for the simple factor, you just have a constant over that simple factor, and you sum them. Right. So one of the factors is a simple factor that repeated, and the other factor is an irreducible quadratic factor that not repeated. Sorry, as an irreducible quadratic factor that repeated and a simple factor that repeated. That is 45.3. So for the repeated quadratic factor, you have as plus b over s squared plus 1, and then you add that to cs plus d over s squared plus 1 squared. And then for the other simple factor, you have e over s plus 4, and then you have plus f over s plus 4 squared. So this giving you a clear idea how to do your partial fraction breakdown, regardless of what the form of the function is given. right? So this one here is a quadratic factor again, right? It's irreducible, and this one is a simple factor, s minus 2, and it repeated. So for the simple factor, you have c over s minus 2 and d over s minus 2 squared. And for the quadratic factor, you have as plus b over, well, this could be slightly simplified as s plus 4 squared plus 1. Because s plus 4 squared is really s squared plus 8s plus 16, and then you add the 1 to get 17. Okay. So at this point in time, let me see if anybody want to ask anything. Any questions at this point? No questions? No. All right. Right. So now we went through all the different partial fraction breakdown, and then in the lecture I also showed you a document where, depending on the form of the function, what the partial fraction breakdown would be. So we went through this extensively. So no matter what form of your function, you're supposed to be able to write the partial fraction and to find your constants, right? So you have here s 4s squared plus s plus 1 over s cubed plus s, right? So this is, you want to find the Laplace inverse of this, but if you notice the denominator, you have a common factor in s cube and s. So what you could do, you could pull out a s there in the denominator, so you end up with s into s squared plus 1, right? 4s squared plus s plus 1 is your numerator. So you end up with a simple factor s and an irreducible quadratic factor, which is s squared plus 1. So you break up that into bs plus c over s squared plus 1. And now you multiply across by s squared plus 1. So notice if you do that here, your left hand side will just have 4s squared plus s plus 1. And then your s will cancel here, so you'll get e into s squared plus 1. And your s squared plus 1 will cancel here, so you'll just get bs plus c by s, right? Right. So sometimes it has become a little complicated to substitute values for s in order to find your constants. So in this case here, it might be easier to collect terms in s squared and equate them, terms in s and equate them, and so on, right? So what I have here, I have a plus b, are coefficients on the right of s squared. C is the coefficient of s on the right, and a is your coefficient of s to the 0, right? Remember, s to the 0 is 1, so that is like a constant then, right? So if you notice on the left-hand side, what is your coefficient of, s squared on the left-hand side is 4. So a plus b is equal to 4, right? If I equate coefficients. The coefficient here is 1, and your coefficient here is c. So if you equate them, you'll get c equal 1. And then the a now is your coefficient of s to the 0, and your coefficient of s to the 0 here is 1, so a is 1. So we get c and a directly by equating coefficients, and we get a simple equation here for with a and b to find b. All we do is we put in a equal 1, right? So that means b will be 3. right? So you have A is 1 over S plus 3S plus 1 over S squared plus 1. And now you apply your linearity property. So you have the Laplace inverse of 1 over S, right? And you could break this up as 3S over S squared plus 1 plus 1 over S squared plus 1. So you could pull the 3 on the outside. You'll get 3 L inverse S over S squared plus 1 plus L inverse 1 over S squared plus 1. Right. So the Laplace inverse of 1 over S is 1, because this is t to the 0, which is 1. The Laplace inverse of S over S squared plus 1 is cos t. So you'll get 3 by cos t, and the Laplace inverse of 1 over S squared plus 1 is sine t, right? And t is greater than 0. So you have that result there, right? After we do the partial fraction breakdown there and we equate coefficients, right? So now we using the table again to find the Laplace of 5 over S minus 3 to the power 4, right? So this here involves a shift, right? So we're using the shift property here. Now look at it carefully. Look at this property here. The Laplace inverse of y S minus a is e to the at Laplace inverse of ys. Now, if you notice here, the S minus 3 to the power 4, right? Is real. You could look at this as 5 over S to the power 4. If you didn't add the minus 3 in the denominator, it will just be 5 over S to the power 4. So you shift by 3 basically, right? So your ys minus a, your 3, your a is your 3. Now we know the Laplace inverse of this here, right? What is your Laplace inverse of 5 over S to the power 4, right? We know that the Laplace of t to the power 3 is 3 factorial over what? S to the power 4, 3 plus 1. And that works out to be what? 6 over S to the power 4. So this kind of similar to the 5 over S to the power. The only thing now, in order for us to get 5 here, what you have to do? Right? You have to put 5 on the bottom here, and you put 6 here so that they will cancel. Or the other way around, basically. 6 here and 5. And you put your 6 here. Right? So if you do that there now, you know, this is 6 and the 6 will cancel. And the 5, you'll get your 5 over that. But this here, we know the Laplace inverse of this is t cubed, right? So look at what we're doing here. We take the Laplace inverse of 5 over S minus 3 to the power 4. And we use this property here. Your a here is 3, so e to the 3t. Right? The Laplace inverse of 5 over S to the power 4, because when you apply the shift property here, it gets rid of this a here. So you're taking just the Laplace inverse of 5 over S to the power 4. Right? So now you have to pull out your 5 on the outside and your 3 factorial. So you have to divide by 3 factorial, which is the same 6 here. Right? And we know that this here is t cubed and 5 over 6. So you'll get 5 over 6 e to the 3t by t cubed for t greater or equal to 0. Right. 44.9. Use table L to find L inverse of e to the minus 2s over s minus 9, right? So here again, we are applying the Laplace inverse e to the minus s t naught ys, right? Where we're using the heaviside function, t minus t naught, and the y of t minus t naught. So y is your function and h is your heaviside function. So what I'm doing here, I'm breaking up the Laplace inverse in terms of your e to your power, which is your minus 2s, so your t naught will be 2. And you're multiplying that by 1 over s. Right? Now remember, the inverse of the Laplace inverse right, of 1 over s minus 9. We know that this is what? We know that this is e to the 9, e to the 90, right? So basically, this is your yt, right? Because the Laplace inverse takes a function in a variable s and carries it to a variable t. So your yt is e to the 90. So according to the rule here, when you find the inverse of the Laplace inverse rather of e to the minus st naught ys, right? If your yt is e to the 90, your yt minus t naught would be what? Where t is here, replace it by just like any other function, this will be e to the 9 t minus t naught. And we know our t naught already. Our t naught is 2. So that will be the heavy side at t minus 2 e to the 9 t minus 2. Right? And remember, the heavy side is remember the heavy side step function, right? So if this is 2 here, right? If you go all the way up to 2 here, in this region here, the function is defined to be 0. And once you pass 2, the function goes up by 1, right? So from here, it will be defined to be 1, right? So if I just say in here, if I put this is 1 here, right? So this is your ht axis and this is your t axis here. So once the function reach 2, anywhere from 2 and under, it will be 0. And anywhere from 2 and beyond, it will be 1. So therefore, you could break up this here using the piecewise definition. So if you multiply 0 by e to the 9 t minus 2, you'll get 0, right? So between 0 and 2, the function is 0, because 0 by anything is 0. Beyond 2, the function, the heavy side is 1. So you're going to be multiplying 1 by e to the 9 t minus 2. So that is how you get e to the 9t minus 2. Right? And in a lot of problems, you'll have to be able to do that to break up a piecewise function into the areas that it defined and apply the Heaviside function as a difference of functions, which we went through in the lecture, right? So you have to be able to write the function as a difference of Heaviside functions. So we're coming up to some examples involving that just now. Using table L to find the Laplace inverse of e to the minus 3s into 2s plus 7 over s squared plus 16. Right? So again, we could just write this, break it up linearly. Pull the 2 on the outside, you take the Laplace inverse of e to the minus 3s by s over s squared plus 16. And then the other one, you could break it up as 7, right? E to the minus 3s, right? 7 by e to the minus 3s over s squared plus 16. Now watch out this little trick here. I'll pull out 7 over 4 and I'll put 4 here. Because I want to use the ruler and know about the Laplace inverse of this. Remember this 16 here is 4 squared. So there's going to be the sine 4t, right? And this here will be cos 4t, right? So I pull off 7 over 4 on the outside here in order for it to scale back and get 7 on the inside. So here now, my t naught is what? 3. So it will be 2 by the heavy side at t minus 3, right? That is the same rule we using here, you know, from up here. So using this here, the Laplace inverse of e to the minus s t naught, and your t naught is 3 here, so you're taking 2 here multiplied by the heavy side at t minus 3, and then you're taking your function t minus t naught. But your yt here will end up being cos 4t. So wherever t is, you replace it by t minus 3. And similarly here, your yt here will be sine 4t. So you replace your t by your t minus t naught, and your t naught here is 3 as well. So t minus 3. By the heavy side at t minus 3. So this is the Laplace inverse here of this function. Okay, graph the function ft equal h at t minus 1 plus h at t minus 3 for t greater or equal to 0, where ht is the heavy side step function, and use the table L to find the Laplace transform of ft, right? So what you have here, you have the sum of 2 functions, right? Now, this first function here, right? Remember, going up to 1, your t naught is 1, right? So anything from 0 to 1, this could be 0. And this one here from 0 to 1 will also be 0, because this one could only step up when it reached 3. The first one could only step up when it reached 1. And the second one could only step up when it reached 3. So if you're defining both of them in the region between 0 and 1, this one will be 0 and this one will be 0, right? Now, if you're defining the sum of the both of them in the region between 1 and 2, well, of course, when you reach 1, this one will step up to 1. Not 1 and 2 rather, but 1 and 3, right? Between 1 and 3, you reach 3 here, this one will still be 0, right? this one will only step up from 3 and beyond. So therefore, in the second region here, t between 1 and 3, the function is 1 plus 0, which is 1. In the first region is 0 plus 0, which is 0. Right? And in the third region, what will happen? Right? The third region, which is beyond 3, both of them will be defined to be 1. So this could be 1 and this could be 1. Right? So 1 plus 1 is not 2. So that is how we able to write this here as a piecewise function. So based on the information given here, right, between 0 and 1, based on the Heaviside rules here, the sum of both of them is 0. Between 1 and 3, the sum of both of them will be 1, and between 3 and infinity, or beyond 3 and beyond, the sum of the both of them will be 2, right? And how you define it when you're writing f t in order to find the Laplace transform? What you do? This region here, you call it f1t, right? If you go through it carefully in the lecture notes, you'll see for yourself. Right, this region is f1t. This second region here is f2t. So to write the entire function, you write it as the difference of Heaviside functions. So the first region, right, that is this region here, right? So that will be what? H at t minus 0, which is ht minus h at t minus 1, multiplied by what the definition of the function is here, and the function is 0. So it will be, when anything you multiply by 0, you won't get any contribution. So I just basically left out that region. The second region here now, between 1 and 3, right? You're taking h at t minus 1 minus h at t minus 3, and you're multiplying it by the function, which is 1. You see it here? Right, on top here. And the third region, you're just taking the function at the Heaviside at t minus 3 at 3, and then you're multiplying that by the function, because this is the last region here. You're multiplying it by 2. So the first region didn't give any contribution. So what you'll be getting here, you'll just be getting the Heaviside at t minus 1 minus the Heaviside at t minus 3 plus 2 times the Heaviside at t minus 3. Now notice this is a Heaviside at t minus 3, and this is a Heaviside at t minus 3. So this is like a 2 in front, and this is a minus 1. So this will give you just a Heaviside at t minus 3. And then you have your Heaviside at t minus 1, which is essentially what we had at the beginning. Right? That is what we had at the beginning with the problem. So I'm just showing you how to work back and derive it then. So you take the Heaviside, the Laplace of the Heaviside at t minus 1. And the Laplace of just the Heaviside t minus t naught is e to the minus s t naught over s. So this will be e to the minus s over s. And this one will be e to the minus 3s over s. And s is greater than 0. And then if we sketch the graph, you see here, between 0 and 1, you have a horizontal line on the t-axis, right? And this is the ft axis here. Right, between 1 and 3. Sorry. All right, so this is a little error here, right? So I want to do some repair here, right? Right. So between 0 and 1 is defined to be 0. So this part here correct. Between 1 and 3, it defined to be 1. So this should really be extended here. So this should come. This should come all the way here. Right. And then from here now, from 3 and beyond, it should be 2. The arrow should be going like this here. Right, so just know that correction here. Right? So what I'll have to do here now, I'll have to change this here, right? So this is the graph here. Right, so that is the graph there, the piecewise function. And the labeling here should be 2 here, right? Okay. So 44.12, graph the function f of t is equal to t into h t minus 1 minus h t minus 3, right? Now look what I put an important note on top there. So I have to multiply t by h into t minus 1. So th minus 1 sorry, t of h t minus 1. This could be written as h t minus 1, right, into t minus 1 plus 1. Because notice what will happen here, the t minus 1 and the plus 1 will cancel each other. So you'll get back this here, t by h t minus 1. But if you use your distributive property, right? If you do use your distributive property, you gotta multiply this term by this term. And then you'll have to also multiply this term by the second term, right? So it will be ht minus 1 by t minus 1, right? And ht minus 1 by 1, which is just ht minus 1. So t of ht minus 1 is really this on the right hand side here. H at t minus 1 plus h at t. Now, in order to find the Laplace, this you can't find the Laplace how it is here on the left. So you have to expand it like how it is here on the right. Right? And similarly, this part here with the h t minus 3 by t. This is going to be h t minus 3, right? Plus 3 by h t minus 3. And well, both heavy side expressions will have negative because you have a negative on the outside. Right? So that is something important to note when you're expanding these things in order to find the Laplace inverse. So we have here, graph the function, right? So the function here, between 0 and 1 will be 0. Because both of them both functions won't step up. The first function will step up when it reach 1, and the second function will step up when it reach 3. So both of them will be defined to be 0 between 0 and 1, right? Now, in the second region, the first function, ht minus 1, will step up to 1, but the second function will still be 0, right? So what you'll get 1 minus 0. But you have to multiply it by t. So 1 minus 0 is 1, and then you'll get t. So t is what the function is defined as when t is between 1 and 3. And then from 3 and beyond, both functions will be 1, right? So 1 minus 1 is 0. So t by 0 is 0. So that is how we get the piecewise defined function here, right? So now what I want to do, I want to use my Laplace of my Heaviside rule here, and then I want to expand this here now, right? Remember, I already expand the first part, so the Laplace are ht minus 1, t minus 1, plus h at t minus 1. And when I expand the second part with the t, ht minus 3, I'll get minus ht minus 3 by t minus 3 minus 3h at t minus 3. So now I could apply the Laplace to that, right? And when I do that now, I'll get the Laplace at ht minus 1 t minus 1 plus the Laplace at ht minus 1 minus the Laplace at ht minus 3 t minus 3. Subtract 3 times the Laplace at h t minus 3, and this here is e to the minus s over s squared, right? Because your t naught here is 1, so e to the minus s, and your function here is like t. So your Laplace at t is 1 over s. 1 over s squared, sorry. So that is why you get e to the minus s over s squared. The Laplace at t minus 1, h at t minus 1 is just e to the minus s over s. The Laplace at ht minus 3, t minus 3 is minus e to the minus 3s over s squared. And this one here, minus 3 by e to the minus 3s over s. Right? And s must be greater than 1. And this is your graph here, right? So I think I have this graph correct. Between 0 and 1, the function is 0, right? Between 3 and 1, the function is t, right? So if it's t, it means that the gradient is 1, right? So when you go from, the rise is 1 and the run is 1. So when you go from 1 to 2, you go up by 1. And then you go from 2 to 3, you go up, you go across 1, you go up 1. And the intercept here is 0, so it had to be coming through here, the origin. So that is why it had to step up. And then beyond 3 is 0, 3 and beyond, right? Okay, so let's just do a couple more here before we end off for the day, and we'll continue again next week. So graph the function f t is equal to 3 into ht minus 1 minus ht minus 4 for t greater or equal to 0, where ht is the Heaviside step function, and use the table to find the Laplace of ft. Right. So remember, you want the difference of these two Heaviside. Between 0 and 1, both of them will be 0. So between 1 and 4, this one is 1 and this one is 0. So you'll get 1 by 3 is 3. And 4 and beyond, both of them would be defined to be 1. So you'll get 0 again. 1 minus 1 is 0. So this is how it's piecewise defined here, right? Now you just have a constant here, so you don't have to expand the heavy side here. It's just to work out 3 times the Laplace of h at t minus 1 minus 3 times the Laplace of h at t minus 4. So this is 3 e to the minus s over s minus 3 e to the minus 4s over s for s greater than 0. And this is the plot here of the function here. Between 0 and 1 is 0. Between 1 and 4, the function is defined to be what? 3. So look at here. And from 4 and beyond, the function is defined to be 0. Right. The graph of ft is given below. So 44.17. Represent f of t as a combination of Heaviside step functions and use the table to calculate the Laplace transform, right? So what I did here, I break up the graph here into 4 regions. So in this first region from 0 to 2, I'm calling it F1. So F1t is 0 here. Between 2 and 3, I'm calling it F2t, so I'm defining it piecewise. So notice here the run here is 1 and the rise here is 1. So the gradient here is 1. But the intercept here is not cutting the axis at 0 here. If this line continues, it will be cutting the axis at -2. So F2t is defined to be t minus 2. F3t is 1 and F4t is 0. So if you break up your function into the difference of Heaviside functions, right? You're going to be breaking it up into functions that you're multiplying by 0 here in the first instant and 0 in the last instant. So you won't get any contribution. You will just get contribution in this region here, F2t and F3t. So this basically will be the Heaviside, right? So let me show you here. Ft as a combination of Heaviside step functions, right? So watch it here. This region here, right? You have to multiply it by t minus 2, and that is between 2 and 3. So that is the Heaviside at t minus 2 minus the Heaviside at t minus 3, multiplied by t minus 2. And then you add it to this one here, the third function. That is the Heaviside at t minus 3 minus the Heaviside at t minus 4 by 1, right? So now here, you'll have to multiply t minus 2 by this function here. So you have h at t minus 2 by t minus 1. And then you'll have to multiply t by h at t minus 3. So that is this here. And then you have to multiply minus 2 by minus 1 here, which will be plus 2h t minus 3. Come out a little light, but you're supposed to be able to make it out. I wrote it in blue ink, and then I scanned it. So the blue ink didn't come out too bright enough. Are you all seeing it? You could just write something in the chat if you're seeing it. Or if I had a trace over for you to see it better. Seen it there? Okay. All right, good. So somebody said they could see it, right? So the ones that kind of, light, I will trace them a little more. So you'll see them. So this is just the extra work in the background to arrive at the function in the simplest form in order to find the Laplace transform, right? Right, so this is what we get in here. Now recall, right? This one here is okay. So this is HR, right? HRT minus 3 minus HRT minus 4 by 1. So you'll just get HRT minus 3. Subtract HRT minus 4. So that won't have any major difficulty there. So the only one you really have to deal with this is the THRT minus 3. You have to apply the distributive property here. So this one here is what I'm going to deal with it. So the HRT minus 2 by T minus 2. And this one here, writing it as minus HRT minus 3 into T minus 3 plus 3. Notice the plus and minus 3 will cancel, so I'll get back this. But now if I use the distributive property here, right? This is 2 HRT minus 3 and HRT minus 3, so I end up with 3 HRT minus 3 from this term here, the third and the fourth terms respectively. Right? And then I have to subtract HRT minus 4. So now I have to expand this. If I multiply this by T minus 3, I'll get minus HRT minus 3 by T minus 3 and minus HRT minus 3 by 3. So I'll get minus 3 HRT minus 3. And so these two terms here will cancel each other. So I'll get HRT minus 2T minus 2 minus HRT minus 3T minus 3 minus HRT minus 4. So that is the final result there for your FRT. So now once I have this form down here at the bottom, I could apply my Laplace transform. Right? So look, I have it here, HRT minus 2, T minus 2, HRT minus 3, T minus 3 minus, and minus HRT minus 4. So I take the Laplace of this one, the second one, and the third one. And the Laplace of the first one is e to the minus 2s over s squared. The second one is e to the minus 3s over s squared. And the third one is e to the minus 4s over s, because this is just the heavy side alone. And s is greater than 0, right? Okay there. Right, so I wanted to make sure you get that clear there, right? So what happened now, we'll stop there, we'll continue again next week, Wednesday. So I haven't gotten the access to my e-learning as yet. I have it set up, but I don't have the enrollment key as yet. So as soon as I get that, hopefully I will get that, if not today, by early next week. So I will give all your information regarding all your midterm exam, right? Very soon. So I want you to keep looking at the stuff, going through the notes, going through the problems, working through the problems, and going through all the questions that you have at your disposal. I will meet with you again next week, Wednesday, and we'll continue, right? So if you have any questions, you could ask it now. If not, well, we could end. So I'll hold on for if anybody have any questions. right? The midterm wouldn't be in the next 3 weeks, right? Because this is 2 weeks already. And I think the semester is 5 weeks. So I would like to think the midterm would be somewhere by the end of the 3rd week, sometime after the 3rd or 4th week, right? And all that we covered so far, that is what you're being tested in the midterm, right? 10 questions, 2 multiple choice and 8 numerical responses. So you will have that is the format of the midterm. 2 multiple choice and 8 numeric responses. The final exam is just like the normal final exam face-to-face. Like what you did last semester, the face-to-face 2-hour exam. Right, so that is it basically. Any questions again? Okay then, right? So thanks for coming, and I hope you had a productive session. So I'll see you all again next week. Right, the final is the 18th, right? Okay, bye.